The other variant in resistance welding is resistance projection welding. Okay. So, resistance projection welding, so what we do is, instead of making an like for example two flat surfaces, you will always have a problem of a dissimilar thicknesses welding, is not it? Suppose if you have a flat joint, flat plate, and then a bigger higher thickness flat plate welded using an resistance spot welding, you always have a problem. Okay. So, instead of keeping two flat plates, you may also have sort of projections in the thinner sheets. Okay. And because of that, the heat is concentrated, is not it? And you may not, you do not need a higher current to heat up the entire interface, right. And if you are doing a spot welding, individual spots, for example, here you need to have one electrode and other electrode here. So, you may allow to do it, for example, first weld here and then go back with your the machine and this point, and you will have to make another joint. So, instead of doing that, you can make some projections and have a larger electrode with a similar current density what you are doing it in a previous in a resistance spot weld. You can do a welding at multiple points, is not it? So, anyway, the contact resistance, the contact area remain the same as the resistance spot weld. Okay. So, instead of doing it in a sequential manner, so first you do a resistance spot weld here and then move it over the other place and do it again here and so on and so forth. So, you can use a slightly larger electrode by having a projection in one of the sheets. So, you can make a heating here and here, and subsequently you can do a compressive loading at the interface, and this sheet becomes straighter. And the advantage over here is there is a mechanical deformation which can also aid the weld interface formation, right. So, the projection weldings can also be used effectively, especially when we are welding dissimilar thicknesses. And this is done in various geometries, whatever things, for example, single sheets, and you can also do multi sheets to make laminates. Okay. So, in this case, you may also have 3 sheets welded together, and you may also have some projections, and these are commonly used for welding studs or the fasteners. So, these are various fasteners, and they will have to be attached to a solid bed, for example, right. And you can pass the current, and then you will have a contact area leading to contact resistance, and subsequently you can push, make a joint, right. And resistance projection welding with slight modification in the discharge mechanism. Okay. So, you can also make what you call as a capacitor discharge welding, okay, which is very commonly used to weld the studs and the fasteners and thermocouples to any substrate. Okay. So, that we will see in the last slide, right. So, this is clear, resistance projection welding. So, we will have a projection, okay. So, and then we apply a current and then press it, we can make a joint. So, compared to resistance spot welding, these advantages because you can do multiple welds at a single step, right. Good. Okay. So, the other variant in resistance spot welding is flash bed welding, okay. And this is one of the other major variants of resistance welding after resistance spot welding, okay. So, this is known as flash butt welding. The most common application of this welding process is wheel making, okay. So, wheel means the steel alloy wheels, we use it for vehicles, automotives, okay. So, those wheels are all made with resistance flash butt welding, okay. So, the wheel making process is how is done actually. So, you have a flat sheet, it is rolled, okay, and brought into contact to each other, and then in flash bud welding, the mechanism works in such a way that we don't really keep both sheets together in contact. We maintain some gap. Okay, so that's what's shown over here. So we keep some gap between the fairing interfaces, right? And then you pass a current. So when you maintain a gap, obviously when you are passing a high frequency current, you will start arcing, isn't it? So arcing would lead to the melting of the interface, right? The first melting would take place, for example, this is my surface roughness, okay? And when you pass a current, so obviously this point would start melting first, isn't it? So it will start form arcing, and then once it melts it will explode, okay, and then it becomes slightly flatter, for example. And similarly the next point would come and arc, and then this will melt, and subsequently it will explode, and the remaining parts, for example next this part will melt, and ultimately you would make a more or less a uniform interface, isn't it? And during this process, because these are all molten, and you will end up heating these adjoining areas to higher temperatures, isn't it? So you are melting the interface. So obviously the regions next to the molten layer would be at very high temperature. That means that now those region can plastically flow, mechanically deform much easily, okay. So you strike an arc, you melt the interface, and then once you reach the temperature which is sufficient to achieve a required mechanical deformation, and then do an upsetting, okay, right. So you have an arcing and melting the interface, and subsequently you apply a load, and so that, and you have an upsetting, and during this process the molten layer at the interface would be sent out, isn't it, as a flash. So whatever layer is molten would be sent out as a flash, and then unmolten region would coalesce and form the interface. There are a lot of advantages of this process, okay. The advantage one is surface preparations. You do not need to prepare the surface, isn't it? So you will have to bring it together. Even if surface is rough, you have a lot of oxides, does not matter, right. So surface roughness can be overcome, because the moment you start arcing, you will end up melting the surface, and you will make an uniform liquid layer at the interface. So once you make it, you upset it. So whatever liquid is there, it will be sent out as a flash. Even the liquid is oxidized, does not matter. So all the oxides which are there in liquid will also be pushed out, and subsequently the regions which are not molten, okay, the unmolten region would mechanically deform and coalesce, make a weld joint, okay. And this is extremely user friendly process, okay, and very robust process, because the arc heats up, melts the interface, but liquid would not form a joint. So you upset it so that liquid is splashed out at the circumference, and then the mechanical deformation would lead to the coalescence of the interface, forming a weld joint. Yes, clear? And this process is very commonly used to make wheel rims, right. So almost 99% of conventional wheels are made with flash butt welding. And there is another variant of resistance welding which is similar to flash butt welding, which is known as resistance offset welding, okay. And the difference between resistance offset welding and flash butt welding is, resistance offset welding we do not arc, we do not melt the interface, okay. In flash butt welding, it is important to understand difference. In flash butt welding, the interfaces, they are not kept close to each other. There is always some gap maintained in the beginning, so that we can form an arc, okay. So arcing is important, the interface will be molten, okay, and then you do an upsetting. Whereas in resistance offset welding, So, we keep the interfaces as close as possible, okay, and then we heat it up, and in resistance offset welding we do not melt anything, right. So, we do not melt anything, we just heat it up the moment the temperature is reached to a higher level, and then we do an offsetting to form a joint. So, the welding is done in a solid state, there is no liquid involved in resistance offset welding. On contrary, in flash bud welding you always have a liquid at the interface, right, it is clear. So, in the resistance offset welding the welding is primarily done in solid state, okay. So, because of that the interface would be prepared very well, is not it. So, otherwise if you have an oxide, if you have some contaminants, grease, and they would be trapped inside the weld, right, it is clear. So, resistance offset welding is also very commonly used for wires, pipes and tubes, where you keep the interfaces together and then you do an offsetting force, and so that you can do a mechanical deformation at the interface leading to a joint formation. Okay. So, in both the processes if you look at it, so basically the flow of material upon upsetting would takes place in such a way that you will have a mechanical deformation, and most of the cases the interface contaminant are pushed to the flash region, is not it. So, this is slightly after deformation. So, the material is deformed and displaced toward the flash regions. Okay. In flash butt welding it is very effectively done, because whatever it goes out is liquid, is not it. So, liquid would carry all the inclusions, okay, on the contaminants which are there even before welding, and then subsequently if you machine this off, so you make a very nice joint, and then you take the interface contaminants out, you will end up having a nice weld. Yes, it is clear. And resistance offset welding generally the offsetting distance would take care of the contaminants issue, right. So, if you are offsetting for longer distances obviously you also increase the flash distance. So, whatever is it was there before welding would be pushed to outside, right. So, basically you are pushing it, and if you are the offsetting distance higher you will end up sending the interface which was there before welding outwards. So, whatever contamination that happened or it was there, you did not clean it properly, would be sent into flash and you can machine it off subsequently. Yes, it is clear, good. Any questions in these two processes? So, you should always see the difference between flash bud and then resistance offset. Okay, in flash bud there is always arc, okay. Resistance offset is close to solid state welding, right. So, in the flash bud welding we form an arc, weld the interface and subsequently do offsetting. So, the molten interface would be sent out as a flash, and then subsequent mechanical deformation would lead to the joint formation. In resistance offset welding the arcing part is out. So, we will have a heating of the interface leading to decreasing yield stress, and then subsequently with a reasonably compressive load you can mechanically deform the interfaces and coalesce form the weld. It is clear, the differences is very important. So, someone says that the both are same, or so what welding process you are using it, resistance offset welding where the arc is there, then it is wrong. Okay. So, this classification is different. So, there are some problems in both the processes, flash bud and resistance offset. The alignment, geometrical alignment, it should be perfect, it should be coaxial. Suppose if you are welding two tubes by resistance offset welding, if they are not aligned properly you have serious problem, right. Say in this case I have just given a couple of examples. So, if you have the axis of the tubes are not aligned properly, so obviously you will end up smearing the pipes, okay. And this is the very common problem even in wheel making. If there is small misalignment and you have an say 2 mm, 2.5 mm sheets that are commonly used for wheels, and so this is one edge of the wheel, and the other edge should be perfect. If other edge is somewhere here, because of the most common problem in the rolling of circular pipes is spring back. Okay, so if a spring back is not controlled properly, suppose so if I extend that, okay, something like this, a cross section. Okay, so anyway, it's not symmetric. Imagine this is a toy car. Okay, so wheel is like this. So now if there is a spring back, obviously, so the joint will be different, isn't it? So now if you are doing flash bedding, the alignment will not be proper. So then there must be an additional arrangement with the clamping, so that now this can be pushed and this can be brought down, so that you will have a perfect interface, and then you can make a joint, right. So this alignment problem is very critical, and there are ways to overcome. So that actually coming from the equipment manufacturer, right, and these problems can be tackled very easily, right. So what else is the last in this variety is actually commonly used for welding fasteners, studs, bolts, okay, into bodies using a capacitor discharge. Okay, so it is like a gun. Okay, so you will have a capacitor giving a discharge of current in a short time, very high frequency as well as in a very amperage current sent at as a short burst, so that it is like in a gun, stud gun. Okay, so in this process the welding is done by rapid release of electrical energy and a very small second, very small time, and then it is extremely rapid process. Okay, each weld would take hardly a millisecond, and then one electrode would be going, for example, I have shown a schematic, the upper electrode, okay, and then there will be a shearing blade. Okay, so it will roll, it will shear like that. Okay, and we have one equipment in our lab to weld thermocouples. Okay, so thermocouples are thin wires welded on a flat sheet, isn't it? So we attach a thermocouple into one electrode. The material to be used will be another electrode. Okay, we pass a positive and negative ends, and then you discharge a current, and then simultaneously you also apply a compressive load. Okay, the electrode is dropped on its own weight sometimes onto the sheet, and the moment you have a contact, a large amount of electric energy is discharged. Okay, so in that process you end up heating the edges, and also there is a compressive load acting on the surface, leading to a weld formation, right. And this process is very commonly used for welding the studs and bolts to the body of vehicles. Say for example, I just showed a schematic, and these are done with the gun. Okay, so if you look at in automotive industries, commonly used in the front below the engine placing. So engines are all engine and the bodies are placed over the fasteners, right. Those fasteners are welded with the bottom panel, and before mounting the engine, if you look at it, or if a vehicle you take out the engine and you just show the bottom panel, there will be lots of studs, bolts attached to the bottom panels, right, and those bolts are attached to the panel by the capacitor discharge welding. Okay, so there will be one robot with like a gun. This can also be done with a gun, hand gun as well. Okay, so you fill with a bullet, which are now studs or bolts, and then you bring it in contact, something like this in this case, and then press the trigger, you discharge the current at the interface. Simultaneously you also use an air velocity, air gun or something like that. The stud will be going towards the piece. The moment you have a contact, the electric current is discharged, and then you melt the interface and form a solid joint. Okay, so this is commonly known as percussion welding, or capacitor discharge welding.